Okay. We'll be getting started in a moment. I'm just giving people the opportunity to get in. It is just 10 o'clock. I will talk about my objectives for today. Number one, I want to review a couple of the free response questions from the practice AP test, which I should be including a couple links in the description. I'm going to update that in a moment. I will eventually update the timestamps so that you won't have to watch through everything in this video. You would be able to just go to the timestamps once I update that and be able to jump to whatever you need. Along with if you just wanted to skip past this kind of initial getting set up time, you could also just do that. But anyway, I see some people are already in the chat. I'm just trying to get the links ready for the first portion of what I need here. Save that then. Save. Okay. If you refresh the stream, yep, there should be two links in the description below. They are the practice test and the practice test and the answer key to the two questions that I'm going to be going over. Lucas, maybe you could answer me this. I'm going to assume I know what this is, but could you describe what is the deal with this notification squad? Where's my problem? I'll give him an opportunity to do that while I kind of get this first problem rolling. So I'm gonna get started. And this video is also going to be saved, obviously, for anybody who has the link to watch it later on, to be able to review the practice problems, and to eventually get the lesson on Chapter 22 of AP Stat. All of those timestamps I will put into the description after the fact. Oh, there we go. I turn notifications on, hit the bell for your channel, so when you post, I get a note. Oh, okay. Well, okay. All right, that's fine. I guess that's what what's his name was saying the other day. I think Griffin said something about notification squad. But anyway, I digress. Like, share, subscribe. I'm gonna jump ahead. Now, there were two problems on the practice test that people were very interested in seeing. Okay, what in the world is going on here on the free response? And they were numbers 4 and number 6. Now, number 4, I would love to talk about. So again, the two links below, they do have, in the description, they have the test themselves. So you guys could easily, obviously, just jump straight to them. But number 4, I'm just going to read it here. You can read it along with me. A survey organization conducted telephone interviews in December of 2008 in which 1,009 randomly selected adults in the United States responded to the following question. The question being, at this present time, do you think television commercials are an effective way to promote a new product? You know, I should probably turn my light on. There we go. Much better. And then the question, of the 1,009 adults surveyed, 676 responded yes. But then in a December 2007 survey, 120 randomly selected adults responded yes to the same question. Do the data provide convincing evidence that the proportion of adults in the U.S. who would respond yes to the question changed from 2007 to 2008? Now, I just need to organize some information here because that's a lot of data that they just threw at us. So ultimately, let me just kind of doodle what this information is, and then we'll kind of go from there. First of all, there is the 2008 survey. Now, the 2008 survey, you could do p hat 08 if you wanted to. I saw that in the answer key. But the 2008 survey had a p hat of 676 over 1,009. Now, for the sake of argument, that is equal to 0.67. We're going to need that for later. A lot of the things that we're going to be doing are going to be rounded a bit later on. But then there was also the p hat 07 survey. That was the survey from the year before. And they gave a fraction of 622 over 1020, which is approximately 0.61. Now, I say approximately again, there's going to be a little bit of rounding error. That's okay. We can deal with that when the time comes. Let me put this up here. This is number 4 from the free response questions, just for the sake of argument. Now, these numbers are going to come in handy. I'm also going to need later on some Q hats. So the Q hat from 08, 0.33. Again, this is just an approximate number. And the Q hat from 07 is going to be 0.39. Again, not exact, but we'll deal with that as time moves on. Now, the question. Let me just go back to the question one more time. Do these data provide convincing evidence that the proportion of adults who would have responded yes to the question changed from 2007 to 2008? Is this a convincing enough change? You're going to have to run, at some point, a 2-proportion z-test. Now, we're going to have to go through the assumptions, conditions. We're going to have to go through all of that. But first, we need to state an appropriate hypothesis. Now, the hypothesis in this case, now again, you can go in any order. It doesn't really matter. But since I've labeled them as such, I'm going to do it like this. My null hypothesis is that nothing is going on. My null hypothesis is that nothing has changed. My null hypothesis is that there's no difference between the 2 years. Now, if you notice, again, I used the hat for the actual sample statistic, but when you get to the hypothesis test, you have to use the population parameter notation. Now, we're trying to see, is this convincing data, is this convincing evidence that the proportion of those who responded yes has changed? Meaning, context of the problem, my alternate hypothesis, because of the wording of that question, has to be written as such. It has to be written as not equal to. Now, with that not equal to, again, we'll deal with that when we get to the calculator with the 2-prop z-test. There's a couple different ways that you can do this, either by hand or with the calculator, but again, we'll get there. Let's do assumptions and conditions. Sump, condish. Let's see how this works out. Now, both sample sizes, 1,009, 1020, we could say 1,009/1020 are large enough samples. That's expected. We could say that, now, it's going to be a little bit weird because of the numbers that we have here. I've already pre-calculated these for myself. Make sure that that number is correct. Yes, it is. Cool. But 676 is greater than 10. successes. The opposite of that, the 676 up to the 1009, that would be, I believe, 333. So 333 is greater than 10 failures. Yes, we have to check all of these. Your assumptions and conditions are vital. You have to make sure that you have hit them before you move on. 622 greater than 10 successes. And the other number I had was 398. 398 greater than 10 failures. You have to make sure each of them are greater than 10. You have to. You have to. Now, beyond that, let's see. Random selection will in the problem itself. Random selection stated. It was stated for both problems, or both surveys, I should say. Now, the 10% of the population, you could say that 1009 and 1020 are less than 10% of U.S. adults. Of course, their population. But now, independence. Independence is a little weird. Independence has to be looked at from two different perspectives. Independence, yes, within the surveys themselves. Independence has to be assumed, or can be assumed, from person to person, their responses, the independence of individual responses. But you also have to assume or infer independence between the two surveys, meaning one survey's result didn't affect the other survey's results. So there's two different ways to talk about this independence. I'll abbreviate independence adult responses. I guess you could word it like that. Independence of adult responses assumed, and independence between two samples assumed. Again, I'm kind of shorthanding it there, but you do have to assume those things. They're very important that you do assume them. Now, because of all of this, because of all of these assumptions and conditions that were met, we are allowed to go ahead with a 2-prop Z test, a 2-proportion Z test. This is what we wanted to do. This is what we needed to do in order to move forward with this problem. Now, you can do this directly on the calculator, and I will show you on the calculator what it looks like. Absolutely, yes, I will. But I will also show you by hand how it can be done, because I need to show you a huge difference between these, the interval calculation and the test calculation, especially the 2-proportion. So we are going ahead and we are going to be using a 2-prop Z test. Let's see what that looks like in the calculator real quick. Two-prop Z test. Now, obviously, I've already inputted my information. Let me just put zeros in for all of them real quick, just so you can re-enter them, because I entered them in a little bit differently compared to yesterday. But since I went ahead and I put the 2008 survey as the first sample, I'm going to have to put the 2008 survey results as X1 and N1. So in this case, it would be 676 and 1009. That was the 67%. And the 622 and the 1020. That was the 61% from 2007. Not equal to. And then we go ahead and calculate. No, actually, let me write the information down. If I'm going to actually perform the test, I want to make sure that I have written down this information, especially for the AP graders. Again, I don't know how they're going to do that in terms of the test you're taking, but we'll see what happens. So I would do X1 as 676, N1 is 1009, X2 is 622, and N2 is 1020. I would do P sub 1 is not equal to P sub 2 in the calculator. And then when I calculate it, look at that p-value. That p-value is what you want. That p-value is what you want. I will also point out this regular p-hat at the bottom right here. We're going to need that in a little bit for some of the calculations that I'm going to show you. But again, we'll deal with that in a little bit. Let me just write down this p-value and then come to a conclusion. The p-value that I got was 0.0048. 0.0048. Now, because of that, that is low. That is lower than 0.05. That is lower than 0.01. Because of that, we have enough evidence to reject. Now, I'm going to come back to these calculations in a little bit, and I'm going to show you how the 0.0048 still plays in a rounded sense. But let's just do a conclusion real quick. Because p-value is so low, you could even put like, 0.0048 is less than 0.05. We reject the null hypothesis. Always make a statement of rejecting or failing to reject. But now we got to go back, and we got to go back to the context of the problem and actually state some kind of proper conclusion using the context of the problem. We are rejecting the null hypothesis. The null hypothesis was that there was no difference or no significant difference between the two samples. So we have evidence to suggest. Now I want to go back to the wording of the question. Let me just go back to I'm clicking on the file right now. Do the data provide convincing evidence that the proportion of adults in the U.S. who would have responded yes to the question changed from 07 to 08? I want to make sure I use that kind of language in my conclusion. We have evidence to suggest the proportion of U.S. adults who would respond, quote, yes, has changed from 2007 to 2008. Now, you could go into a little bit more detail. What did they respond yes to? The particular question they were asking was about, do you think television commercials are an effective way to promote a new product? You could say that we have evidence to suggest a proportion of U.S. adults who would have responded yes to that question, stated if you want, has changed from 2007 to 2008. Now, I'm saying it has changed, but again, I'm saying we have evidence to suggest that it has changed. I'm not saying that it actually has. But that would be the proper conclusion to that question. Now, I went ahead and of course, the way that I am, instead of using the calculator, I decided to go ahead and try and do this thing by hand as well. Now, I want to make a clear distinction here. This is the end of that problem. This is everything that you could have done, and that would have been perfectly acceptable to answer number 4 on the free response of that particular test. But I wanted to show you something. 2prop z int versus 2prop z test. You see, when you are calculating the 2prop z test, your calculator is using a normal CDF. And in order to do the proper normal CDF, you have to have a proper standard deviation, or standard error in this case. Now, for our problem, this poses a little bit of a weird thing. A weird, not weird dilemma, but like a weird thing. When you are dealing with 2prop z int, the standard error is needed in order to do the interval. But the way that you would calculate that standard error is you would take the individual standard error of the first sample, square it, take the individual standard error of the second sample, square it, add them together, and then square root them back. That's the idea of going from standard deviation to variance, and then back again. So, for the interval, that is exactly what we do. Now, again, I'm using the numbers that I had before, the 0.67, the 0.61. I'm using those numbers. But it would basically be 0.67 times 0.33 over 1009. That would be the 2008 sample. Squaring it would get rid of the square root, plus 0.61 times 0.39 over 1,020. Again, square root, same issue, going away, bye-bye. And then you square root it back. You would get a standard error of, well, basically, whatever this calculates to be. Now, let me just see what it is real quick. 0.67 times 0.33 divided by 1,009 plus 0.61 times 0.39 divided by 1,020. Square root that answer. Ho-ho! You get a standard error of 0.021, we'll round it to, something like that. But if you are doing the 2-prop z test, you have to work with the null hypothesis assumption. The null hypothesis for the test was that there was no difference between the two. There was no difference between the two. Samples, that is. And if you notice, again, when I performed the 2-prop z test, you can see it right here. There's the p hat sub 1, that's the 2008 sample. The p hat sub 2, that's the 2007 sample. And then just a p hat. The p hat was the pooled result. It was the pooled result. Basically, in order to get that pooled result, they did the following calculation. They pooled all these numbers together, and they got approximately 0.64. Now, the assumption is there is no difference between sample 1 and sample 2. There's no difference, according to the assumption that we have. So, when you calculate the standard error for this particular 2-prop z test, you have to calculate it in the following way. Notice the decimals at the top. There's the first sample. The first sample size with the 2 decimals at the top based on this pooled result. There's the second sample, and then putting them together. That's what this thing does. It is super weird. Again, let me just knock out this calculation real quick. Now, somewhat negligible in terms of its calculation. Let me bring back the previous calculation. There we go. Square root that answer. Boom. Well, I'll do it that way. And that was like 2.7. There we go. So there's the main difference between the two. It seems negligible, but in some problems, it could make a real difference. When you are doing the test, you're assuming there's no difference between the two, so you have to pool the results. If you're doing the interval, you don't have to worry about pooling them. You don't. If you ran through the normal CDF using this as your standard error, it would work. It would absolutely work. You're looking at there being no difference between the two. Now, currently, there's approximately 6% difference between the two. So if you were going to do normal CDF, you're looking at a 6% difference or greater, assuming that there should be no difference, with a 0.02131 as your standard error. You can see we do get a tiny number, 0.0024, but wait a minute. The alternate hypothesis was not equal to. And because it was not equal to, in fact, let me draw this out so you can kind of see this right here. I'll draw this thing out just so you can see exactly what I'm referring to with this problem. There we go. Cool. We assume a difference of 0. We assume there is no difference between the two. The standard error that I'm getting is what, approximately 0.021 change. So wherever the 0.06 is, the 0.06 would be like out here. There we go. So that would be like a difference of 0.06 or greater. Now that would be 0.06 in the positive direction. But because we said not equal to, it could be 0.06 in the negative direction as well. So when I do this calculation, when I do normal CDF, 0.06, comma, big number, assuming a mean of 0 and a standard error of 0.02131. This gives me approximately 0.0024, which only accounts for that area. I have to double it. If I were to double it, there is the number that they wanted. Doubling it results in a p-value of 0.0049 if you rounded it up. But that's still evidence to suggest that you would reject the null hypothesis. Again, this is number 4 on the free response. Weird. But I love this problem. I love this problem. Now, I'm not going to go into too many details about number 6. I'm not going to go into too many details about number 6 because some of it does have to do with the lesson that we are learning today. And again, if you have questions, please, by all means, ask your questions. And I will get to them when there's an appropriate time to take like a little bit of a, I can take a question there. But let's talk a little bit about number 6. Actually, you know what? Let me save some paper. I took a lot of stuff from my classroom. I did not take enough paper. I should have taken a couple of reams before I ran out the building. That was a traditional Mr. Markey sip of coffee, too. Let's talk about number 6 before I lose my mind. Okay. So on number 6, again, the links are in the description for the practice test that you can get to. But I'm just going to read it out. 2 students at a large high school, Peter and Rania, wanted to estimate mu, the mean number of soft drinks that a student at their school consumes in a week. A complete roster of the names and genders of the 2,000 students at their school was available. Peter selected a simple random sample of 100 students. Rania, knowing that 60% of the students were female, and selected a simple random sample of 60 females and an independent simple random sample of 40 males. Both asked all of the students in their sample how many soft drinks they typically consume in a week. Describe a method Peter could have used to select a simple random sample of 100 students from the school. I'm assuming that most all of you nailed this first part. Again, I didn't see your individual responses. I was only able to see your scores when you submitted them to me. But there is a complete roster and name of the names and genders of 2,000 students at the school. So you could say something along the lines of, okay, assuming that the roster is alphabetical, assign each of the students, actually no, write each student's name on a piece of paper, put them into a hat, shake well, and then pull out 100 names and survey those students. Like, that's perfectly acceptable. You could also number the students from 1 to 2,000 and use a random number generator to select 100 names and then the numbers associated with the names of those students you would sample. Again, I'm going to assume part A was correct for most all of you. The interesting thing is when we get into B and C. Was there a D? Yeah, there was a D. We'll deal with the D in a minute. B. Peter and Rania conducted their studies as described. Peter used the sample mean x bar as a point estimator from mu. Rania used x bar equals 0.6 x bar female plus 0.4 x bar male as a point estimator from mu, where x bar female is the mean of the sample of 60 and x bar male is the mean of the sample of 40. Oh, wow. My battery is already at 55%. How in the world did that happen? I'll have to plug in soon. All right, I'll do that after this problem. We'll take a little break. I'll be back shortly or something like that, but after this problem. So let's see. Summary statistics shown below. Number of soft drinks. This is for Peter. He surveyed 100, and he had a mean of 5.32 and a standard deviation of 4.13. It's the sample standard deviation. Okay. Based on the summary statistics, calculate the estimated standard deviation of the sampling distribution, sometimes called the sampling error of Peter's point estimator X. Some of you may be a little bit like, what? But this is partially what we're going to be getting to. Partially. Actually, no. This was, I can't remember the name of the chapter, but it was it was a sampling distributions or something like that. I get. But basically, what it comes down to for part B, this is number 6, free response question. Part B, you would take his standard deviation and divide it by the square root of the sample size. That's honestly all it came down to. Now, yes, 4.13 is not a population standard deviation. It's a sample standard deviation. Again, this is partially what we're going to be getting to. But dividing by the square root of the sample size is what you needed to do for that problem. I think it's like 0.413, I want to say it is. Because you're dividing by 10, right? I'm not losing my mind. You can't lose something that you didn't actually have. Yeah, 0.413, of course I'm correct. That's good. Part C. Circle. Part C. Summary statistics for Rania, and there's her table below. Based on the summary statistics, calculate the estimated standard deviation of the sample distribution of her point estimator. Okay. I can understand why on part C, most to all of you would have been like, what the heck is going on? Understandable. But let's talk about this. For Rania, for female, her sample standard deviation was 1.8. For males, her sample standard deviation was 2.22. Now, she eventually, let me go back up a little bit. If you back up to the top of that page, it said that Rania used that calculation, x bar overall equals 0.6 x bar female plus 0.4 x bar male as a point estimator for mu. Well, if that is the case, then if you're talking about the change in her standard deviation, the change in her standard deviation would be 0.6 times the 1.8 and 0.4 times the 2.22. Little weird, I know. But ultimately, and I'm not going to do the full calculations just yet. I'm just going to kind of show you what it looks like and then show you what the answer looks like. But 1.8 would have been over the square root of 60. But then because multiplication division affects standard deviation, you would have had to multiply it by 0.6. Same thing for the males, except it's 0.4. You would have to do 0.4 times this particular sample standard deviation. Again, more details to come in the next chapter. But because multiplication division affects standard deviation, you would have to do those multiplications. Now, you are to add them together. Because you're adding them together, you can't add them together in their standard deviation form. This is going to get a little weird. But ultimately, you would have to square them, then add them together, then square root them back. This is a very weird thing. Let me just kind of show you what it would look like on the calculator real quick. I'm going to do them individually. Yeah, I'll do them. Maybe, let's see if I can do it all at once. I have no idea. 0.6 times 1.8 divided by the square root of 60, close, squared, plus 0.4, no, parentheses 0.4 times 2.22 divided by the square root of 40, close parentheses, squared, square root that answer, I get 0.198. And if you go to the answer key that was provided for you, 0.198 is exactly what they did. Now, they didn't do it, they didn't show it exactly the way that I did it, but this is the way that you would have to go about doing it. Just what it comes down to. Weird problem. Just a weird problem. Finally, part D showed you a bunch of dot plots. Using the dot plots above, I'll explain why Rania's point estimator had a smaller estimated standard deviation than the estimated standard deviation at Peter's point center. Now, if you look at the actual dot plots, you can see that Peter's dot plot contains both male and female. They're all mixed together. But in Peter's sample, you can see two kind of peaks, whereas in Rainia's, there were two separate dot plots split into female and male. Peter's is much more spread out. Remember, standard deviation is a measure of spread. Peter, because he kept both male and female combined, the standard deviation was much, much, much more spread out. Because, in general, according to Rainia's results, if they hold true for Peter's, men drink more soft drinks on average than females. So everything's going to be spread out from 0 all the way up to, what was Peter's, like 17 or some junk like that? Whereas for Rainia's, the female distribution, well, the standard deviation was quite small. And because she separated the males was also somewhat small. You can see that here, 1.8 for the female, 2.22 for the male. And then when she combined them, weird. I know. Just a weird, weird situation. Compared to Peter's 0.413. Yeah. Anyhow. That was number 4 and number 6. So what I'm going to do, I'm going to take a short BRB. I have to get a phone charger because right now my phone is at 45%. Okay, so we're going to do a BRB in, let's call it 5 minutes or less. Call your neighbors, call your friends, have them join the stream. I'll be back in a little bit. I just got to get that charger. I'm going to keep it running. Oh, I should play intermission music. I read it. I read it now, unfortunately. Well, I am back. I am back. Everybody wake up your friends. Everybody wake up your classmates. Get them to join the stream. Everyone click that like button. Like, share, subscribe. Because we're about to get moving. Who else is here? I see Jacob and Lucas. That's about it. Maybe I should tweet about this. Like, hey, I'm live. Oh, look, there's McKenna. When I do this top-down directly from my phone, there's not as much of a lag, thankfully. Thankfully. Turn this down. I could probably turn that down. Yeah. Sorry, I'm getting like a ton of messages. Gonna turn that on. Camera being you, of course. All right. Good and good. I just want to check. You can all see me, right? That's cool. How about you scroll through Reddit if you're using your phone to stream? I'm not gonna scroll through Reddit. What are you talking about? Why in the world would I scroll through Reddit? Okay. Now, like I said, for those that are not here, I am going to include timestamps so that they don't have to watch through 43 minutes of me going over a couple problems and 5 minutes of just blankness. But I'm going to include those timestamps so that they can just move on and get to the important parts that they need to get to. Just honest question to those of you that are here right now. On a scale of 1 to 10, 10 being the worst, how bored are all of you this week? I just want to see your answers in the chat. On a scale of 1 to 10, 10 being the worst, how bored are you all right now? Or this week in general? Oh, follow-up question. I like your numbers. Follow-up question. Compare that to what you are normally. So like put like normally this, but now I'm a this. Just for this. I just want to say. I know. wait. That's funny. Oh my gosh. I'm sorry. I'm just laughing at Lucas's math there. Normally a 2. Right now a 5. Overall a 9. Oh my gosh. That makes me laugh. A bit. I don't know. Oh, goodness gracious. What am I going to do with myself? Okay, I'm holding steady at 43%. I have like 50 unread text messages right now from my fellow teachers, and I'm a little bit like, I don't want to read any of them. Yeah, I know what you meant. Throughout the week, overall, yeah. But like right now, 5, like I've brought that down a bit, so we'll kind of see how that goes. Fun fact for those of you that may or may not be interested, I'm not going to be live streaming tomorrow, but I am going to be filming myself tomorrow because there is a worldwide, technically worldwide. There's a cubing competition, online for the first time, and they're doing something. If you go to cubingathome.com, I'll put the link in the chat in a moment. But if you go to cubing, there it is, cubingathome.com. They're doing an online competition for quarantined cubers. And there are, where I gotta look at this now, there are 4,643 people signed up. That is insane to me. But I'm going to be competing in that tomorrow from about 11 to 2 or something like that. There's no chance I'm going to win, but it's something fun that I'm going to do. My son's going to join me at one point, but again, I'm not going to live stream that. I'm just going to film it and then I'm going to post it on because I have to have video evidence of my solves for various things. So, why'd he say hey? He said, "Hey, I'm in suspense right now." Oh gosh, that's true. You could say that you're 100% confident that the sun will rise tomorrow, but then there is a small chance that an asteroid will hit the planet. Let's just say that I'm 99.9% a positive I'm not going to win. Anyway. Okay. I'm going to get started. So again, if you do have any questions during the lesson, please, by all means, ask them in the chat. I will address them as best I can. What is my fastest time solving the cube? In competition, my fastest solve is 12 seconds. But in practice, my fastest solve is roughly 8 seconds. I'll post a link right now to some of my records. Paste. There you go. If you guys click on that link right there, it'll take you to my official World Cube Association page with the number of competitions that I've been to and my personal records within each event. And you can see my national rank, my continental rank, and my world rank. Right now in the world, I'm ranked roughly number 15,000 and change for single, but I'm under 15,000 for average, which I'm actually kind of proud about that. My average was under 15, so mine was like 2 minutes, bruh. Hey, you know what? Maybe we'll figure out in the future if this thing lasts a lot longer than it has so far, which I'm assuming it will. Maybe I'll do a few. Well, I don't know how I would do that. How would I do a cubing tutorial? Unless I had like multiple streams coming in at once or some junk like that. I don't know. But anyway, I could do a cubing tutorial and I could walk people through things and have them ask questions and junk like that. And whatever. I need to get started with math. You all got me sidetracked with cubing. Weirdos. Anyway. I know Lucas and Jacob have been waiting for this. It has been far too long that they have not heard these words spoken by me. But if you're here, or if you're watching at a later time, I'm going to need those notebooks out and open. Anyway. Wait, what? Let's go! Oh my gosh. This whole time at home has got me so messed up. Anyway. As a side note, you're talking like guttural screech, like ee, like something like that. My wife and I just started watching The Mandalorian, and we're like 4 episodes in right now. And I refused, before I watched this, I refused to buy into the Baby Yoda hype. But since we've only watched 4 episodes, every time he's on screen, I feel like the world gets brighter. That's poetry. Anywho, alright. This is chapter 22. I'm gonna call the... You know what? My paper's weird. I'm gonna keep it like this. I don't care. Chapter 22. I'm gonna call this Sample Means and T-Testing. Today is March 27th. Man, I have no idea. I have no idea how long it's been. Oh gosh, this is really nice. Anyway, a long time ago, I gave you guys a chart. in terms of what type of testing or intervals that you would need to do. And I'm just going to recopy that chart off to the side right here for a moment. Basically, well, what kind of tests do you need? I'm going to shorthand this. And then the question became whether or not you had categorical data or quantitative data. Categorical data dealt with proportions, and quantitative data dealt with means. Proportions you would deal with the letter P. Means you would typically deal with the letter mu. Now, if you had proportions, regardless of whether or not it was a 1 sample or a 2 sample, does not matter. You would end up using a z-test, whatever that ended up being. This is a shortened version of what I wrote into your notes of whatever. Anyway, for quantitative data, however, it really depended on whether or not you had your population standard deviation. So you could say you have sigma, sigma being the population standard deviation. If you had sigma, you can still do a z-test. And I'm going to show you something on the calculator in a few moments. If you don't have sigma, then you would not be allowed to do a z-test. You would have to do a t-test. I also have an anecdote to kind of go along with this in a moment. We'll get there. Showing you in the calculator real quick. If I go over to tests, under z-test, you can see right here, there's a mu and there's a sigma. That's the population parameter. Now it says list, whatever, that's if you actually have the data to type in. I'm going to go to stats, and then that would be the sample data that you would actually do. We'll deal with that. If you have a graphing calculator with you today, this would actually be very helpful. I'm going to show you a few things with the calculator. But if you go to t-test, when you go to t-test, they do have a mu again, but they do not have a sigma. If you don't have sigma, if you don't have a population standard deviation, you have to go towards t-testing. Now, this is the same for t-intervals. You can see 2 sample, same deal. Even z-interval versus t-interval. For the z-interval, sigma. For the t-interval, you don't have sigma. You have to be very aware of that. But this is where this chapter comes into play. Now, in your textbook, you can read this later, but make a note for yourself if you want to read this later. On page 576 in your textbook, there is a story about Gosset's tea. Gosset, and I'm not gonna read the whole thing. That was a noise. You can read it on your own time, but basically this guy worked for the Guinness Brewery, and he worked testing vats as to their quality and junk like that. Again, there's more details in the story. I haven't read it in a while. I'm just kind of summarizing. The nuts and bolts of it is that if he was going to test it, well, he tested it pretty much by drinking for the most part, but he didn't have enough of a sample size in order to qualify for what we do for z-testing. At this point in time when he was working, they didn't know about t-testing. And what they found out was when you didn't have a large enough sample size, when you did not have a population standard deviation, the z-testing ended up screwing up. And they were rejecting vats of beer that there was nothing wrong with, or they were failing to reject vats of beer that there was something wrong with them. And ultimately, he went back to school and studied statistics, studied, and he figured out through his studies this idea of t-testing. And it has to do when you don't have a large enough sample size and you don't have a population standard deviation. It's a huge part of statistics. Close that off. There we go. So let me just, again, for concrete notes so that I have them for a future date. If you have sigma, which is the population standard deviation, you can use the z interval. Let's just say I'll start with intervals and then I'll backtrack. You can use the z interval, x bar plus or minus z star times sigma over the square root of n. This is how a z interval would be calculated, but you would have to have the population standard deviation. Fun fact, you in real life will most likely never have the population standard deviation. You just won't unless you successfully were able to take a census of something. Who the heck knows? If you don't have sigma, if you don't have sigma, then t-testing and intervals are needed. Now, before you conduct, oh, there's 2020 census. Yeah, I already filled out my census, just so you know. The census won't, mostly changes the congressional districts in the House of Representatives, and because it changes the congressional districts, it actually changes the number of electoral votes that each state has. But that won't take effect until the 2024 election, I believe. Yeah, I've also been, again, bored out of my mind. I've also been trying to get into Ancestry.com, so I've been looking into a lot of old censuses, censi. I'm assuming that's what they're called. Multiple censuses, censi. Anywho, back to this. Now, when you are doing a z-test, whether you're doing proportions or means, you have to do assumptions and conditions. T-testing is no different. You have to have the same assumptions and conditions. You have to. Now, these are going to be a little weird. Assump / condish for quote T. You have to have sense. I don't know. I'm a math teacher, dude. But assumptions and conditions for T. First, censuses. I like censi better. Back to this. You have to have independence. Independence amongst the sample being collected, whatever the concept, like, I don't know, you're collecting people's heights. Each height is independent from the next or some junk like that. I don't know. It has to be a random sample. As always, again, you have to hit these assumptions conditions. Every single test that you conduct, you have to write down assumptions conditions. I feel like assumptions and conditions have been one of the number one things that I have hyped this entire school year. Also, context. I don't know. I'm trying to think of another one, but I can't. Anyway, you should also have the less than 10% of the population as well. Now, again, when you're doing a t-testing, your sample size does not have to be large enough. It does not have to be large enough. T-testing is mainly done when you have small samples. Now, because you're not doing proportions, you don't have to worry about successes and failures. This is not successes and failures. You're just collecting data. But when you have a small sample size, you don't have to worry about it being a large enough sample. There is one more condition. And this one is the weird one. This is called the nearly normal condition. Nearly normal. You have to make sure data looks normal enough. This is one that you're not going to be happy with for the most part. It's like when we did linear regression, and you had to make sure that the line was, quote, straight enough. Normal enough. Do I want to know what Pepiga is? I don't know if I should really Google it right now. What in the world? Am I going to regret Googling this? It's a Twitch emote featuring a distorted image of Pepe the Frog. Oh, come on. You guys are the worst. Okay, I'm going to delete that. I do regret Googling that now, so just for the sake of argument. This is why I shouldn't have Google when I'm teaching. But anyway, these are the assumptions and conditions that you have to hit. Now, there is such a thing as a t-score that we have to be aware of. A t-score is very similar to a z-score. Oh, I'm way out of focus. Can I fix that? How do you fix that? Much better. Cool. We had calculated the z-scores back in the day. And I'm just going to put a little reminder here. This is a little reminder. Reminder. Z-scores were typically calculated as such. Data point minus the average divided by the standard deviation. Well, actually, I should also put this in right here. Yeah, that was for sampling distribution. Because when you had an X-bar, you had a sample. And you had a sample mean, that is. And you would subtract the average and then divide by the standard deviation of the sample, which would be the population standard deviation divided by the square root of the sample size. And that would calculate the z-score. That's what we had to do for sampling distribution. But now we have such a thing as a t-score. Now, I'm going to write a couple things in here, just as a side note, before I get to t-score. Standard error for these t distributions are going to be this calculation. Again, the S is indicating the sample standard deviation. The sample standard deviation, not the population, because for a t distribution, you don't have sigma. If you don't have sigma, that completely changes the rules in regards to what we're doing. But now here's how you would calculate that particular t-score. Put a little box around it. Now, if you notice that little t has a little subscript on there, sometimes you'll see the subscript, sometimes you won't. I'll explain what that subscript is in a moment. I go back and forth behind putting it there and not putting it there. It really depends on the situation. But what that n-1 is, that n-1 is the most patriotic. Wait, I zoned out. What is this? What is what? What is which part? You tell me. Just Jacob, are you even taking notes? Or were you looking at memes? Okay, these equations. I put this up here as a reminder. This is the z-score that we would typically calculate back in the day. He's actually taking notes for once. This is the z-score that we would calculate back in the day. I can't remember the number chapter, but it was like for sampling distributions. For sampling distributions, if you had the sample mean, the population standard deviation would have to be divided by the square root of n in order to get the bottom of that fraction. Another way of calculating a z-score that we would typically do, another way, just alternate way, alt, would be like x minus x bar over s or something like that. Again, if you had a normal distribution with the mean right in the middle and each standard deviation going out to the left and to the right, you can calculate approximately where the z-score would lie, and you could determine whether or not the data point was above the mean, below the mean, and whether it was unusual or not. Now for this is what we call the t-score. T-score. Same concept. Same concept as a z, except you can't use a z. You can't use a z if you don't have the population standard deviation. So we'd have to calculate the standard error by taking the sample standard deviation and dividing it by the square root of n. I'm going to show you an example of that in a little bit. And then to calculate the t-score, you would have to do this. Now, to show you the most patriotic statistic you will ever hear, n minus 1 is, from a vocab point of view, is known as degrees of freedom. When you write that down, you better be saluting. That is called degrees of freedom. The sample size minus 1. America. I had mentioned in the multiple choice review video that I did for you guys that when you were doing linear regression and t-score, t-testing, and all that stuff, it would actually be n minus 2. We may or may not get to that this year because of the circumstances. That would most likely come after chi-square testing. But for the time being, degrees of freedom. America. Just to give you the calculation for the t interval, because I did the z interval on the previous page, the t interval would be calculated in the following way. Very, very similar to that of the z interval, except you would not be doing sigma divided by the square root of n. You would be doing s divided by the square root of n. Oh, there's Paige with a cowboy hat on. Anyway. And then, of course, the s, this is t star, very similar to z star, but dealing with the degrees of freedom. America. Let me see where I'm going with this. Assumptions, conditions, blah, 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 blah. Okay. I am going to put, I'm going to try and put a link. Like, wait, hold on. Can I just use a calculator to find the t interval like I can for the z interval? Yes. Yes, you can. But again, I caution you. Multiple choice questions. Honestly, that's what it really comes down to. If you're doing a t interval or a t test for for a free response, you can absolutely just use the calculator. Just make sure you hit the proper assumptions and conditions. And when you do, you should be fine. And then you can just write down what you put into the calculator and then have the proper conclusion. The proper conclusion for a t-test being either reject or fail to reject, and the proper conclusion for a t-interval, I'm this % confident, blah, 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 blah. We'll deal with that. We will. I wanted to show you a sample problem. I had a sample problem set up. I just got to create the link for you. Where is my sample problem? Crikey. Give me just a minute or two. Talk amongst yourselves. I had a sample problem, and now I lost the link for it, and I have to create the link for it in order to get to what I need for you. So, y'all give me a minute. This is page 9. Okay, there's an error that I didn't know existed. There's another error that I didn't know existed. Okay. Okay. I hate technology with an overarching passion. Okay. Save to my Google Drive. Just page 9. There we go. I'm basically trying to create a document that I want you all to have, and I want to put a link in the description. Okay. So I have downloaded that. Where are my recent files? It's right there. There's the page that I need. Let's move that. to my folder called COVID-19 files. COVID-19 documents. Move it there. Good. Google Drive. It's both the best and the worst. Okay. This is Chapter 22, Sample Problem. And like I said, I'm going to create the link. Share. Make a shareable link. Anybody can view it. Save. Copy. Copy to the clipboard. Almost there. Channel videos. Details. Here we go. Chapter 22, Sample Problem. Save. Okay. Refresh. Oh, there's people talking. It's really nice outside. Refresh your streams. Refresh your streams. And in the description should be a link. And if you can't see it, boom, there's the file link right there. There's the file link that should be in your description. And this is the problem that I am about to go over with you. If you can see it, it should say a professor at a large university. So I don't know if you're on a phone, I don't know if you're on a computer, but that file is there. And if you want to look at that file later after the fact, by all means, look at that file. But that is the sample problem that I'm about to go over with you guys. There we go. Organize my papers. Let's see what my battery life is. 44, not bad. That's what happens when I plug in. Anyway, during a stream, I'm using as much battery as I'm wasting. Okay. So if you have a graphing calculator, this would be helpful. But you don't have to have a graphing calculator for this particular thing. Let's see here. So the problem in question, a professor at a large university, hold on, I'm opening up a link while I'm talking to you. There it is. A professor at a large university believes that students take an average of 15 credit hours per term. Random sample of 24 students in her class of 250 students reported the following number of credit hours that they were taking. Does this sample indicate that students are taking more credit hours than the professor believes? Now, this is a t-test type of problem. It is. And then number 2 is talking about a confidence interval, but I'm going to deal with that in a little bit. But this is a t-test type of problem. So this is the Chapter 22 sample problem. Link is in the description. If you don't see it, just refresh the stream and you'll find it, but it should be there. The professor believes, this is his belief, that the average number of credit hours is 15 per term. So he believes that mu is equal to 15. That's his belief. Could be true, could not be true, who the heck knows. There's a random sample of 24 students in her class of 250. Now, the 250 we don't have to write down right now, but that will come into play later. And they reported the following number of credit hours. Now, in your graphing calculator, I'm going to input that information real quick. Now, you can do that if you want, if you have one. Otherwise, if you don't have a graphing calculator, you can just follow along. I'm just going to double check my numbers real quick. I have 24 in there. 12, 13, 14, 14, 15, 15, 15. Good. Then I have 1, 2, 3, 4, 5 16s. Good. Three 17s, four 18s, three 19s, a 20, and a 21. Good. Okay. So I'm gonna need some information off of this data. If you enter your data into list one, and then you run a 1var stat, it can give you some of the information that we are going to need moving forward. Now, first of all, x bar is equal to 16.625. And S, I don't care about sigma in the calculator. I don't know what that sigma is right now. I don't know. I don't know the population standard deviation. Ignore that sigma. You're not going to need it. You need the S. The S in this case is approximately 2.223. I'm rounding up. Oh, sorry. I need to drink more coffee. I should get sponsorships for this live stream. I think that would be great. Anyway, but this is the information that we need in order to do this problem. Now, it says that we are to test an appropriate hypothesis and state your conclusion. The professor believes that students are taking 15. Does the sample indicate that students are taking more credit hours than the professor believes? We need to state an appropriate hypothesis. The hypothesis is that mu, or the null hypothesis, is that mu is equal to 15. When you are doing your null and alternate hypotheses, you have to make sure that you use population parameter notation. Mu in this case. You are not using x bar. The alternate hypothesis is that the professor believes that they're taking more than 15 credit hours. On average, something like that. Yeah. Anyway. Okay, good. That's the first step for that. Now we have to do assumptions conditions. We have to do assumptions conditions. So, because, well, if we're going to use a t-test, we have to make sure that we hit the proper assumptions conditions. Now, first of all, random sample stated in the problem. Random sample stated. Good. Number two, independence. You could say student credit hours independent from each other feasible. Or it's feasible to assume independence of student credit hours from each other. Because I'm taking 17 credit hours that may not affect you taking 19 credit hours, independent of each other. 24 is the sample size, less than 10% of population. But now here's the deal, which population? If you were reading the problem, there was that number, 250. 250 of students in our class. The professor is only concerned about the students in our class. A professor at a large university believes that students take an average of 15 credit hours per term, a random sample of 24 in her class of 250. Now, yes, you could also assume that the population is students at the university. But, for the sake of argument, the professor is only sampling students that she comes into contact with. So, of the 250 class population, the population is just her 250 class. And 24 is definitely less than 10% of that. We're good to go. But now the nearly normal condition. This is tricky. This is tricky. Because if you're talking nearly normal, you need to look at the histogram. You need to look at the histogram of the data. The best way to do that is with the graphing calculator. Now, I told you I entered in all my data into L1 in order to get X bar, in order to get S. I'm going to need to look at the histogram. And to do that, you go second y equals. I mean, you could also draw this by hand if you wanted to, but why would you? You go into plot 1. Okay. um, let me finish this portion, and then let me Jacob's comment, because it is important that we do that. Turn it on, put it on histogram. We're on L1. Yay, oh happy day. You're going to have to zoom 9 that sucker. There's the histogram. What does it mean to be normal? Normal means symmetric. Normal means unimodal. Having that normal curve, which it does. Yes, there's a gap in the middle, but it doesn't have to be perfectly normal. It just has to be, say it with me now, nearly normal. I'm pretty sure 2 of you just said nearly normal along with me. But let me address Jacob's comment. He said, I'm just going to call it early and say it's nearly normal. For the most part, yes, you can. But that is not going to suffice when it comes to an AP grader. You can't just say, nearly normal, good enough. It's not going to suffice. Because every now and then, you might be faced with a problem that, unfortunately, it doesn't work out. I mean, yeah, it's going to be close enough, as Lucas just said, fluffy language. Yes, it's close enough. It doesn't have to be perfect. But you still have to go ahead and do the legwork. Now, in this case, you could always draw a little sketch. It doesn't have to be perfect. But what I'm literally doing is I'm drawing what I saw in my calculator. Just drawing what I saw in my calculator. And you can say histogram of data is, quote, nearly normal. And what this would do is it's showing the AP grader that you went ahead and you looked at the actual histogram. Now, you can't just draw a random histogram. You're going to know what the data actually looks like. You're going to know. Of course, you could use a different scale if need be, but this is what we basically have. You got to make sure that it's reasonably unimodal and symmetric. It is nearly normal. Yay. Cool. So now, because of all of this, we can use a one sample t-test. In fact, let me do this over here. We will use a one sample t-test with 23 degrees of freedom. Again, salute when you write that. They can tell when you're not saluting. Okay. Where do we go from here? On my graphing calculator, I'm going to have to go to a one sample t-test. Which is basically just labeled t-test. You know. Yay! And I'm going to have to input this information. Now, if you inputted that information into your list, you could just simply do data, and then all of that information would be there. It would be there, boom, L1, yay, oh, happy day, yay, cool. But the beautiful thing about the graphing calculator is that the second that you ran that one var, wait, what was it called? Yeah, one var stat. What am I losing my mind for? The second you use the one var stat, you can see that with the exception of mu, everything else was automatically done for you. X bar, S, and it's all there. Just this. Now, n is still 24. Obviously, that's not your degrees of freedom. N minus 1 is degrees of freedom. I just wrote that for the sake of knowing what it was. Now, I have to change my mu. What did he say? 15? Yeah, 15. He said it was 15. My alternate down here, greater. Now, if you're going to use the t-test, you're going to need to write down this information. Sorry, I don't know what's in my throat right now. Not coffee, that's what. Anyway, for the t-test, mu is equal to 15, x bar is equal to 16.625, s is equal to 2.223, n is equal to 24, mu greater than mu sub 0. If I were to calculate that, boom, look at that p-value. My gosh. Look at that t-score. Yes, that's a t-score right there. I can show you how all these things were calculated in a little bit. But what we need, and I'm going to write down both of these pieces of information, your t-score is approximately 3.58. Oh, Mr. Markey, because the t-score was 3, can we say that that's unusually high? Here's the problem. Your curve for the t-distribution depends heavily on the sample size. Meaning, a t-score of 3.58 with a sample size of 24 means something much different than a t-score of 3.58 with a sample size of like 100. Can you please move the calculator a little? I hope that was fun for you. There you go. Don't you dare sigh at me. I will sigh at you. Anyway. Oh, but I gotta write down my p-value. Now my p-value is some scientific notation number. I'm gonna write down this. 1, 2, 3, 4. That's what that p-value actually is right now. That's important. The p-value means the exact same thing that you have always known a p-value to be. If the p-value is lower than 0.05, that gives you evidence to reject the null hypothesis. Say it with me. If the p is low, the hoe must go. Yes. Yes. Very scientific. But we can come to an appropriate conclusion at this point. We can absolutely come to an appropriate conclusion at this point. Now, boom. Here we go. With a p-value so low, less than 0.05, we can reject the null hypothesis. With a p-value that low, we can reject the null hypothesis. Again, our null hypothesis was that the mu was equal to 15 credit hours. There is, and you could say strong if you even wanted to. You could say there's strong evidence. I'm just going to say evidence. There is evidence to suggest the mean number of credit hours taken amongst the professor's class is greater than 15. With the p-value so low, less than 0.05, you can even say less than 0.01, or even 0.001, we can reject the null hypothesis. There's evidence to suggest the mean number of credit hours taken amongst the professor's class is greater than 15. We have that evidence. There's overwhelming evidence to that extent. Now, there is something else that, again, I just need to address. In some of your graphing calculators, you have these functions: inverse t, tpdf, and tcdf. Some of you do not have inverse t. The TI-83 graphing calculator mostly does not have inverse t, unfortunately. So, in a future lesson, I'm going to show you how to do inverse t, because you would need that if you were going to do the calculation for the t star for an interval. But that's a future lesson. If you don't have inverse t, I'm going to show you how to do that. I'm going to emulate a TA. I don't even think they have a TI-85. There's an 84, there's an 89, there's like a 91. I don't know how they number these things. Shut up. Anyway, in terms of tPDF, we're not even going to touch tPDF. Just like normal CDF, we're only going to use tCDF. Now, you might think that you could do something along the lines of this, where you're like, okay, tCDF, how am I going to use this thing? Well, they were looking at getting, well, their sample was 16.625. 16.625, comma, big number, comma, an average of 15, which is the assumed mu, comma, how do I do this? Mr. Markey, how do I do this? How do I put in that sample standard deviation? Oh no, oh no, oh no. Anyway. You could put in 2.223 as that sample standard deviation. But let's just see what happens here. I just want to show you what happens here, because then what I'm showing you right here may be for a future lesson. Because, again, some of your calculators may be different than others. But if I do this, you do get an argument. There's a reason for that. There's a reason for that. When you type all of that stuff in for tCDF, they do assume that you're doing something with degrees of freedom. Now, in some of your calculators, you have these 4 arguments, typically: lower limit, upper limit, mean, standard deviation. Cool. But for the t distribution, you may have to input either, again, the sample size or the degrees of freedom. It depends on the version that you have. Let me just put in the degrees of freedom. Let's see if we get a similar number. Oh, I get an argument here. I wonder why. It comes down to the fact that tCDF does not work the same way as normal CDF. The way that tCDF typically works is that you're not putting in a lower limit, upper limit, a mean, and a standard deviation. You're not doing any of that stuff. Instead, you have to put in the lower limit, upper limit as the t-score. As the t-score. It's a weird function. If you're doing this on a free response question, I would, as Jacob is saying, absolutely use the calculator to get that done. Make sure you've hit all your assumptions, conditions. Good. Golden. But I am going to have to spend another lesson, not today, but I am going to have to spend another lesson on how to use this tCDF and how to properly calculate a t-score and how to properly calculate a t-star for an interval, which I'm going to finish this problem up, but I'm not going to do that today. Basically, 3.58, comma, big number. Now, again, if I did it right now, it's not going to know what to do because it depends on the degrees of freedom. America. If I put in 23, it gets you the approximate number that we needed. Oh, there's a glare on there. Yeah, but it gets you the approximate number you're getting. See what happens when I do 24. When I do 24, it's off. See, unfortunately, when you do tCDF, you got to do lower limit, upper limit, degrees of freedom. These calculators are weird. Some of you have the 84 calculators where you have like a weird interface where it actually shows you what you're typing in. Those are nice. Again, that's a future lesson. We'll deal with that later. Let's finish up the problem that we have. The problem that we have. on the worksheet that I provided for you at the bottom, they wanted you to find a 95% confidence interval for the number of credit hours taken by the students in the professor's class, and then interpret that interval. This is what we're going to finish up with today. It's the last thing we're going to do today. Thank you for all sticking with me this entire time. The 95% confidence interval. If you were to go to your calculator and go to T interval, let's see what we have to type in. Okay? X bar and S are already there because we ran the one var stat. That glare's killing me. Or a badly timed. Wait, I would. Okay. Sorry, I got thrown off by his comment. Anyway, but the X bar and the S are automatically there because we ran the one var stat. The N is there. Confidence level 95. Let's just see what happens. Boom. Takes a few extra moments, but there it is. So again, if you're going to be doing a T interval, it is important that you tell the AP grader what you typed in. Again, assumptions, conditions. Oh, I hit all the assumptions, conditions. I'm allowed to do a T interval. Cool. But then X bar is 16.625, S is equal to 2.223, N is equal to 24. My C level is 95%. Calculate, and it ends up being 15.686 to 17.564. Now, what this means is the same as it's always been. It's the same as it's always been. The way that the T interval was calculated was based on that formula that we did earlier. Again, that's a lesson for another day where I'm going to talk about T star and all that fun stuff. But this is the T interval. We can say we are 95% confident the true number of credit hours taken in the professor's class is between 15.686 to 17.564. We are 95% confident that the true number of credit hours is within that interval. Which, if you notice, the null hypothesis of 15 credit hours is not in the interval. That is evidence against the null hypothesis. In fact, if you wanted to, instead of running a T test, you wanted to run a T interval, you could do that here and say, oh, since 15 hours is not within the interval, this is evidence to suggest, well, you could say this is evidence against the null hypothesis. You can reject the null hypothesis. This is evidence to suggest that the true number of credit hours is greater than 15 hours. Perfectly acceptable. But again, you have to show all that information and write that proper conclusion and all that fun stuff. Now again, in terms of calculating the T interval, I'm going to show you how to do that another day because some of you have the inverse T, some of you don't have the inverse T, some of you don't even have graphing calculators. What are we to do in that situation? Who the heck knows? I don't know. Anyway, this concludes my lesson for the day. I'm not going to be teaching any new information today. Here, let me try something out real quick. I'm not going to teach math. I'm going to do some silly. I'll be back in like a minute. No, less than a minute. 30 seconds. Haha. Let's see. I wanted to see how well this looks. I don't have the a good computer to kind of show this in real time, but according to what you guys are telling me and whatnot, you can actually kind of see this a little bit. you know. I'm going to be competing tomorrow, as I said, in an online competition. I'm not going to be filming it from this perspective. I'm going to actually have to film it from a side perspective because they want to see me in the video actually accessing the file and the file with the scramble and then scrambling and whatnot. So I'm just going to scramble this up a little bit and then see how this goes. There we go. I'm just scrambling up a 4x4. You're hyped? Good. You should be hyped. Scramble, scramble, scramble. Again, if you're going to be stuck inside, learn how to solve a Rubik's Cube. Hey, you know what? Just for fun, let me see if I can find the proper link to this. I'm going to post a link for you. Guys, if you're really interested in learning how to solve the Rubik's Cube, if you're really interested, I do have a video. Boom. There's the link to it right there. Now that video that I just posted the link to, it has scrambles, not scrambles, I'm sorry, algorithms, it has directions, it has timestamps. You can use that video to basically learn how to solve the cube. And I guarantee you, if you follow those directions, you will be able to solve the cube in less than a couple of minutes. With practice, of course, practice, within like a week or less. Pretty much you could spend the rest of today watching that video, and by the end of today, if you spent enough hours doing it, you would, you'd be able to do it. It's really great. Look at that cube spin. It's just wonderful. Anyway, would you all agree this is sufficiently scrambled? I don't have a timer. Yeah, I don't have a timer. I typically use my keyboard. When I'm trying to scramble. I'm just rolling up my sleeves now. So, let's see here. Oh, cool. Yeah, but it looks cool. So I'm just going to go ahead and inspect. Hopefully you'll be able to see what I'm doing in real time, but we'll kind of see how this goes. Wait a minute. Do I want to do that? Do I want to do that? That will go down to that, and then, okay, cool. Here we go. Ready, set, go. There we go. No, I'm stuck. I'm not stuck. I just needed to get the proper colors in place. Man, I'm out of practice. I have not competitively solved a cube in such a long time. It's kind of, not sad, but I just don't have time for it anymore. Like some of these kids who like they practice like constantly and they make videos for them solving the cube. Yeah. There we go. Yeah, that was terrible. I really need to practice if I'm going to a competition tomorrow. Here we go. I'm just going to walk through that right there. There you go. Come on. That was minute 1. Lame. I'm supposed to average, like, I want to average down near, like, 50 seconds. I don't know. Anyway, I can also solve it blindfolded, but of course you can't see that at the moment. Not this cube. I can't solve this cube blindfolded. I can solve the regular 3x3 blindfolded and the 2x2 blindfolded, but that's about it. But yeah. Anyway, I'm also considering live streaming old school video games. I have a setup where I have the camera on me, and you can see on the screen there'll be multiple windows and stuff like that for streaming, live streaming speedrunning video games. Again, when my kids go to bed and my wife goes to bed or doing other stuff, what am I doing if I'm not like teaching or grading or cubing or jumping off a building or something like that and then flying? I don't know. Any other questions before I go? Because I'm going to end this stream smash. No, I can't stream smash, actually. The reason why is I don't have the proper hookup for the Nintendo Switch. I need, like, there's like an $80 hookup that you can do in order to like, what do they call it? Like video capture? Like, I don't have a video capture card on this computer. If y'all want to start, no, why would I even ask that? No, that's ridiculous. There's other causes to give money to. I would not, um, yeah, give money to people who actually need it, you know. But anyway, are there any questions before I kind of sign off for today? Um, Again, with my YouTube channel, you can, if you want to, if you're really bored, you can just look through some of the videos that I have on my YouTube channel. It's not just videos on the TV show Lost. Eventually, I do want to do random things, but we'll see how that goes. Anywho, all right, it's been fun. Wow, hour and a half. I gotta go eat some lunch or something along those lines. But I hope you guys are doing good. I am going to post the video to the Google Classroom soon, and well, no, the link is already there. Yes, so I am going to put the timestamps in, hopefully after lunch. So if you're someone who is watching this video, please, yeah, the timestamps will be there, so no worries. Anyway, thank you guys, and hopefully we'll have another live stream lesson next week. See you then.